Hello, in this lesson we are going to talk about a new topic in rigid bodies, which is known as the Euler angles. And to introduce this topic, we need to remember that, we are working on a rigid body here, and that, we have two coordinate systems to locate a point in the rigid body. One is an inertial frame that doesn't move. It's like always at the same point while the rigid body is moving, and the other one is a coordinate system that is fixed to a point in the rigid body. Okay, so it is moving with the rigid body. So remember that there was an equation that relates the components of the bases that correspond to each coordinate system. We have been using the coordinates prime to express the basis of this coordinate system, and not prime for this coordinate system. And that equation is that EI prime is equal to A J I prime EJ. Okay? Remember, this basis corresponds to the to this coordinate system. Like maybe any point in this coordinate system can be expressed as a linear combination of the elements of this basis. We can express this as EJ, which is the basis E1, E2, E3. Okay, in this case, E1 will be maybe this unit vector that points in the x axis. Yeah, because actually E1, can be seen as the x, but, we just name it as E1. In this case, this will be E2 and this E3. And then for this coordinate system, we will have that this is E1 prime, E2 prime, and E3 prime. But I'm bringing this back to memory because the important thing here is that remember that there is a transformation matrix that relates these two bases. So we are going to work again with this matrix. Okay, and an important thing is that this matrix, it depends on the configuration of the elements that compose the rigid body. And these elements A, which are the elements of the matrix, they depend also on the time. Okay, so we know that we can maybe express a change of basis if we make a rotation of the coordinate systems. Okay, so in that case, this matrix will represent the transformation matrix that, for example, in the case of we want to make a rotation about the x-axis, for example, let me call that matrix Rx, and we are going to rotate an angle theta. Well, that matrix, it is a very famous result that this matrix can be seen as 1, 0, 0, 0 cosine of theta minus sine theta, 0 sine theta cosine theta. So what we are going to do in this video is to consider that the transformation matrix A is made of a product of three rotation matrices. Okay, that's why we are going to introduce the Euler angles, because these are going to be the angles of rotation that are going to be for a rotation, actually two rotations in the z-axis, or about the z-axis, and one rotation about the x-axis, which is going to be given by this matrix. So in other words, we are going to define the matrix A as R, Z, phi, Rx theta, R, Z, gamma, like this. This is the product of three rotation matrices, but recall that we are making two rotations about the z-axis. So this is going to be the transformation matrix that we are going to be working with. Okay, another equation that will be important in this lesson that we have been using in recent lessons is that a dot ki prime a kj prime is equal to the Levi-Civita symbol ijs omega s, where omega represents the components of the vector of angular velocity. So if we see this equation, we can take a a matrix representation of this equation given by a dot transpose, because again, this element is the transpose of this. Recall that this I, well, is on the column position of the element. So this means that this is the transpose of this matrix. And we are taking the derivative with respect to time, which is equivalent to take the derivative with respect to time of each element of the matrix. And here we are going to multiply by A, and this is going to be equal to, well, some matrix that will represent the, well, its elements are going to be the angular velocity components, but we will see that on the second part of the lesson, actually. The important thing here is that, well, we need to calculate this quantity over here. So as you can see, well, there will be so many calculations because, well, we need to take the transpose, then take the derivative, and then multiply. So, and we have a product of 3 matrices. So, yeah, maybe it will be a bit big calculation. So let's begin. First of all, recall that the transformation, the rotation matrix about the z-axis is given by this matrix over here. Cosine of phi minus sine of phi, 0 sine phi, cosine phi, 0, 0, 0, 1. Okay, so if we want to rewrite A in terms of the product of these matrices, we are going to have that A can be seen as, and I'm going to be using the copy-paste function a lot in this video, I think, maybe. Just not to write every matrix. Yeah, well, this corresponds to the RZ phi element. Well, what happens with the Rx theta? Well, we have it here, is this matrix that I'm copying right now. And then, well, the matrix that corresponds to the gamma variable, well, it's just going to be the same, but instead of using phi in this matrix, we are going to use the gamma variable. So that means that it will be this one, but we are going to switch this phi for a gamma, like this. Perfect, so this is our matrix A. So we need to take the transpose, actually the derivative first. So, okay, well, yeah, and to take the derivative first, we are going to do it using this expression. And, well, yeah, well, we have a product of 3 functions, 3 matrices that its variables depend on time. So that means that if we take the derivative with respect to time, well, we are going to get that A dot is equal to, well, let's take the derivative of the first, and then this is going to multiply the second and the third matrix, then plus RZ of phi, Rx theta dot, RZ gamma, and then plus RZ phi, Rx theta, RZ phi dot, of course. Perfect. And then, well, we need to take the transpose. Let me use this parenthesis just in this moment. So what are we going to get? Well, you know that the transpose of a sum of matrices, well, it's the sum of the transpose matrices. I said it right. It is yeah, that the transpose of a sum is the sum of transpose. So that means that we need to take the transpose on every element that we have here. Let me do this for you to be able to see it easier. Taking the transpose is taking the transpose on each element. And also remember that if you have a product of two functions and the transpose of that product, well, is equal to BTAT. Okay, we need to switch the order of the product and then take the transpose on each element. Okay, so the trick to do it with three functions is to do it first with the first function, the first factor, and then do it with the second factor that is going to be taken as the product of these two matrices. So we are going to get the product of these two transpose times this matrix transpose. Something like this: Rx theta RZ gamma transpose, and then RZ phi transpose, like this. And then, well, we need to take the transpose again on this product. So that means that, well, we need to switch the order of the factors again. So that means that we are going to get here Rx theta and here RZ gamma, and then these two transpose like this. Okay, so as you can see, these Rx, it ends again in the middle of the triple product. You see that it began at the middle and then it finished at the middle again. So we just need to switch the order of these matrices that are first on the left and on the right. So we switch the order. And remember that these are z phi, well, it has a dot here. Perfect. So after explaining this with the first term, we are going to use the same rule for the second terms. So if we do that, we are going to get RZ gamma transpose, Rx theta dot transpose, and then RZ phi transpose. And then for the last element, we are going to get RZ phi dot transpose, Rx theta transpose, RZ phi transpose. Okay, perfect. Yeah, I think we are going on a good way. Then, yeah, this quantity tells us that, well, we need to make the multiplication. So, okay, well, we are going to calculate that. We have that a dot t times a, well, it's going to be equal to all this thing times a, but a is this. Okay, so let me write the complete expression just for not to get confused. Let me copy this big thing. Okay, here we have that the term that corresponds to a dot transpose, and then we close this parenthesis here, and then we multiply by a, which is RZ phi Rx theta RZ gamma. Okay. Okay, if we do this, well, we just need to split the product into these three terms. We are going to get this, yeah, times RZ phi Rx theta RZ gamma, and then plus, then the second term, which is this, then that is going to multiply RZ z phi r x theta r z gamma. Okay, and then plus this element times r z phi r x theta r z gamma. Okay, and here something interesting is going to happen. Remember that the transformation matrices are orthogonal matrices. So that means that R inverse is equal to R transpose. So looking that the transpose is the inverse, for example, let's see here, we have that this product, the transpose times the regular matrix, well, is going to be equal to the identity matrix. So yeah, this is going to be like canceling this product. Then here we have the same thing. We have the transpose of RZ times RZ. So we are going to get the identity matrix here. And then it will happen the same when we multiply Rx with Rx, because we have the transpose here. So this one times this one is going to be the identity matrix. So the final result of all this is just going to be Rz dot transpose times Rz gamma. Okay? And I think that's the only thing we can simplify. So if we do that, we are going to get that this is equal to, let me copy all this, because I think that there is nothing we can simplify from this expression. So it remains the same. And then the second expression is going to be Rz of gamma transpose Rx dot theta transpose Rx theta Rz gamma, and then plus Rz dot of gamma transpose times Rz of gamma. Okay, so by now we can set that this is equal to A dot transpose times A, and well, we need to calculate every term of this equation. So let me switch the color just for not to get confused. And we are going to start by calculating the product Rz dot of gamma transpose Rz gamma. Okay, so what is this going to be? Well, we have that, well, here we are going to have some matrix, which is the derivative and the transpose, times, well, Rz gamma, that we know it is cosine of gamma, minus sine of gamma, 0, sine gamma, cosine gamma, 0, 0, 0, 1. So here we need to take the derivative first and then take the transpose. So let's make it in one step. What are we going to get? Well, when we take the derivative of each element of this, by the chain rule, we are going to get a gamma dot, because remember, if you take the derivative of the cosine of gamma with respect to time, of course, we get minus sine of gamma times the derivative of gamma with respect to time, but that is gamma dot. And we are going to have that in every term of these, well, in these 4 terms that we have here. So we are going to take out a common factor of gamma dot. And then, well, we need to take the derivative on every element with respect to gamma. So, and then take the transpose. But remember, if we have the element that is on the first row and the first column, if we take the transpose, this element is going to remain the same. So here we are just going to get the derivative with respect to gamma. And then we take the derivative with respect to gamma of this, which is going to be minus cosine of gamma. But the position will be here, minus cosine of gamma, because it's the transpose. It will happen something similar here. The derivative of sine is cosine, so we get here cosine of gamma, like this. and then the derivative of cosine of gamma here is minus sine gamma. Of course, here we are going to get 0 again, 0 again, 0 again, 0, and the derivative of 1 with respect to time is 0, so this becomes a 0. Perfect. Okay, so what are we going to get? This is going to be gamma dot, and if we multiply, we have minus sine cosine plus cosine times sine, so this first element is going to be 0. Then we have minus sine squared plus cosine squared. This minus with this minus is a plus actually, so we have sine squared plus cosine squared, so that is 1. Here we are going to get a 0, of course. Then minus cosine squared minus sine squared, we are going to get minus 1 here. Then plus cosine sine minus cosine sine, which is 0, 0, 0, 0, 0, of course. So yeah, this is, and I don't know why I switched the color of the pen. Let me recall that this is R Z dot gamma transpose R Z gamma, and we are going to maybe close this to keep the result to use it later on. Perfect. So we are going to continue by calculating the product Rx theta transpose Rx theta. So again, here we are going to get some matrix, and then here we have Rx of theta that we know it can be defined as 1, 0, 0, 0 cosine theta minus sine theta, 0 sine theta cosine theta. Okay, so again we need to take the derivative with respect to time, and I need to say that this was missing a dot here. So, well, first of all, we need to take the derivative. So again, we are going to have a theta dot as a common factor here. The derivative of 1 is going to be 0, 0, 0, 0, 0, like this. And then, well, the derivative with respect to theta of minus cosine is going to be minus sine theta. The derivative of minus sine is going to be minus cosine, but remember that we take the transpose, so this element corresponds to this position here. So again, the derivative of the sine is cosine, so it goes here, and the derivative of cosine is minus sine. Perfect. So this is going to be theta dot times, here we are going to get, of course, 0, 0, 0, 0, 0, and then minus sine times the cosine plus cosine times the sine, that is going to be a 0 here, plus sine squared plus cosine squared, it will be 1 here, then minus cosine squared minus sine squared, it will be minus 1 here, and then plus cosine sine minus cosine sine, it will be 0. Perfect. Again, another important result that we are going to use later on. So let me switch the color again. Now we are going to calculate the next. It will be Rz of gamma transpose Rx dot theta transpose Rx theta Rz gamma. Why are we calculating this? Well, because here, well, that is what we need to calculate. This term that corresponds to the A dot transpose times A. So we are going to calculate this whole piece that we have here. By now we already have this, and we are finding this in this step. So the last part is going to be to calculate the first element, which is the longest element. Perfect. So what happens if we calculate this? Well, this is going to be equal to, look that here we have Rx dot theta transpose Rx theta, which is actually this thing that we just calculated. Okay, and Yeah, we can write theta. Let me take the theta dot here, and then this is going to multiply some matrix, and then the matrix that we just found, 0, 0, 0, 0, 0, 1, 0, minus 1, 0. And then this is going to multiply RZ gamma. But RZ gamma, well, it is, remember, cosine of gamma minus sine gamma, 0 sine gamma cosine gamma, 0, 0, 0, 1. And then we have calculated, actually no, it is just the transpose. Yeah, so it is easy. We just need to take the transpose of this matrix. So we are going to get cosine of gamma, sine gamma, 0, then minus sine gamma, cosine gamma, 0, 0, 0, 1. Perfect. Okay. So let me just tell you what is the result if you make this triple product of matrices. You will get a 0, 0, sine gamma, 0, 0, cosine gamma, minus sine gamma, minus cosine gamma, 0 here. Perfect. Okay. Another important result. Okay, so, well, we need to keep making calculations of products of matrices. So what is the next calculation is the last one, the last piece, which is the longest piece, the one that is, remember, RZ gamma transpose, Rx of theta transpose, RZ of phi dot transpose, RZ of phi, Rx theta, RZ gamma. So this is going to be equal to, look that here we have RZ dot of phi, and that matrix had a common factor of phi dot, and actually is the only matrix that has a common factor that we can take out. So that means that this whole product will have a common factor phi dot here. And then we are going to start writing these all matrices. RZ gamma transpose, well, it was this one that we have here. So it is cosine gamma, sine gamma, 0, minus sine gamma, cosine gamma, 0, 0, 0, 1, times Rx theta transpose. That matrix is 1, 0, 0, 0, cosine theta, sine theta, 0 minus sine theta, cosine theta. Perfect. Then RZ of phi dot transpose, well, that matrix, I think it is, well, it will be this one, but instead of gamma, we will be using phi. So we will get minus sine phi, cosine phi, 0 minus cosine phi, minus sine phi, 0, 0, 0, 0. Perfect. And remember that this all multiplies a phi dots, but we already put that variable here. Perfect. And then, well, these multiplies RZ of phi, which is cosine of phi, minus sine phi, 0, sine phi, cosine phi, 0, 0, 0, 1. And then this multiplies Rx theta, so that is 1, 0, 0, 0, 0, cosine theta minus sine theta, sine theta, cosine theta, and then this is going to multiply RZ gamma. So that will be cosine gamma minus sine gamma, 0, sine gamma, cosine gamma, 0, 0, 0, 1. Okay, perfect. Something that you need to notice, that I want you to notice, is that when you make this multiplication of these two matrices, remember, well, yeah, they only depend on the phi variable. So what we are going to get from this is a matrix that will not depend on the phi variable. Actually, it will be a matrix with only constants. So why is that? Because if, for example, you get a minus sign of phi, cosine of phi, and then plus cosine of phi times sine of phi, well, in that case you get 0. And on the other cases you will get something like sine squared plus cosine squared, and that is 1. So it will happen all the time in this product. So that means that the entries of the result of this product is always going to be constant. So that I mentioned that because the result is only going to depend on theta and gamma. And well, yeah, that matrix will be only of two variables, but it will be multiplying actually phi dot. So a very curious fact. So I'm not going to make all these products, but I'm going to tell you what is going to be the result. Of course, we are going to get a phi dot here, and here we have 0 cosine of theta minus sine theta cosine gamma minus cosine theta 0 sine theta sine gamma sine theta cosine gamma minus sine theta sine gamma 0. Okay, perfect. So this is the final important result. So it is this one that is equal to this. Okay, and if you remember the big formula that we found, well, we need to sum all these results that we got. So yeah, to do that, let me write that A dot transpose times A is going to be equal to, well, first of all, this whole matrix, this, and then this is going to sum, well, it will be this matrix that we have here that corresponds to this product. Okay, so we are going to get, let me copy. Okay, there is the matrix, and then, well, we need to add the matrix that corresponds to this product that we have here. Okay, because remember, this is the last piece of the elements, so we need to add to the sum this whole matrix that I'm copying here. So let me put this here. Okay, perfect. So we are about to get to the important result of this video. What happens if we sum? Well, I think this is easier because it's just a sum of matrices. So if we do this, we are going to get a big matrix that will be 0 here. It will be theta dot cosine, sorry, phi dot cosine theta plus gamma dot. Then here we are going to get minus phi dot sine theta cosine gamma plus theta dot sine gamma. Then here minus cosine theta phi dot minus gamma dot 0 phi dot sine theta sine gamma plus theta dot cosine gamma. Then theta dot sine theta cosine gamma minus theta dot sine gamma. And here, yeah, I think it is very hard to do it respecting all the space. So here we have minus phi dot sine theta sine gamma minus theta dot cosine gamma, and then 0 here. Okay, first thing to notice, this is the negative of this, and this is the negative of this. Of course, it happens the same thing with these two elements. Okay, so by now we are going to finish the lesson here, and just let me tell you that this matrix is going to correspond to a matrix whose elements are the components of the angular velocity vector. Okay? Yeah, actually, because remember that we established this equation here. So that this is telling us that this product of matrices, well, they can be seen as another matrix whose entries are, well, the elements of the angular velocity vector. So that is what we are going to use on the next lesson. And by now, just let's keep this result because we are going to use it later.